Sizing feeders. Um, Jeff, if you remember, our project was a 500 amp panel. We brought the service to it, and then we took a feeder, a 100 amp feeder for the 100 amp panel receptacle, and we took 225, was it 225 amp feeder to feed the 225 amp panel. That's what this chapter is doing. So you guys are ahead of this chapter. The only reason I would like you to read it, get different ideas about what we have done. We have sized feeders. We're going to review a few things about sizing feeders. When you read the chapters, do the questions, guys, hopefully, and listen to me, and you do it for the project, it will sink in. So feeders, the NEC code book, I always tell when I teach the code, I always say, guys, there are 3 circuits in the NEC code book you must understand. Service entrance conductor circuit, that's Article 230. 215 is the feeders, and 210 is the branch circuits. These are different terminology that the code use. Okay, so the first thing I would like to talk about when we're sizing feeders. Everybody knows what the feeder is. Feeder is the conductors between 2 overcurrent protection devices. That's really what the feeder is. A conductor is between 2 overcurrent protection devices. You're going to see in a second. Okay, feeder loading. We'll talk about feeder loading and feeder calculation. Determine the minimum overcurrent protection device. So I have my feeder here, and my feeder is feeding a panel, and you guys are going to size the conductor and the overcurrent protection device. Done. That's what basically this is supposed to do. Determine the size of the feeder conductors, the overcurrent protection device. Determine the appropriate correction and adjustment factor. Correction and adjustment factors based on bundling and temperature. Any comment, any question about this, guys? I have, just to summarize, I have my 100 amp panel, and was it number 1? I think we used number 1 with it, right, Jeff? We used number 1 to feed 100 amp. That's it. That's what this chapter is all about. When it comes to feeder, guys, then they talk a little bit about correction factor for temperature and adjustment factor for temperature and bundling. You'll be a fool if you put conductors, feeders, not branch circuit, feeders, multiple feeders in one conduit. You'll be a fool, literally. Even though the code allows you to do that, don't you ever put feeders, dedicated circuits, dedicated conduits for feeders. Can I have thumbs up, Chad? Don't get into the derating, and you don't get into any problem, especially feeders. Why? Because they're carrying a huge amount of energy. You don't want to bundle them. Branch circuit with you, feeders no. So that's what we're going to be talking about. Calculated voltage drop. I promise you guys, when I do voltage drop calculation a little bit, when it comes to feeder, a couple of things, guys, you have to be very aware of. A couple of things. Number 1, you guys size the cables for me, no problem. We size the cable based on the load. Number 2, we have to size it based on the voltage drop. We didn't talk about sizing based on voltage drop. So you have to pay a little bit of attention about sizing a feeder based on voltage drop. Now, why is the voltage drop becomes a big issue, guys, for feeders? Because feeders are long. They tend to be long, 100 feet, 200 feet feeders. The longer the feeder, the more that you have to pay attention to the voltage drop. I promise you we will be doing calculation on the voltage drop issue. But when I size my feeder, here's my feeder overcurrent protection device. Here's my panel here, my 100 amp panel, my number 1 conductor, my 100 amp overcurrent protection device. Now this is based on the overcurrent, the distance. Can you guys see the distance from here to here? This is based on a shorter distance, probably what? Less than 100 feet. Now this is the distance between the overcurrent protection device and the panel. As the distance gets longer, then you have to pay attention to, typically 100 feet or larger, you have to pay attention to the sizing based on voltage drop. What does that mean? You might have to go and up this one to 1 aught because of voltage drop. This continued to be 100 amp. This continued to be 100 amp. The only thing that we upped is what? The conductor because of voltage drop. Can I have thumbs up, Chad? How do you do the voltage drop calculation? I'm sure we've done it before, but I will be doing examples how to size based on voltage drop calculation. Okay? So when it comes to feeder, Jeff, the simplest way of sizing is based on the load. Done. After you size based on the load, you ask yourself, are the panels 100 feet away from the source or more? If they are, then you're going to do a voltage drop calculation based on the load. A voltage drop calculation. Meaning, you're going to ask yourself, can number 1 carry 100 amp for, what's the distance? You're going to pick up the distance where the panel, say, for 200 feet. Yes, with a voltage drop of, what's the voltage drop? 3%. With maintaining a voltage drop 3% or less? If yes, then your size is good. If it's not, what do you need to do? Oops, a bit one size. That's why, Aaron, when you go to engineering firms, you're going to find that they go to 100 amp, they go always higher than the conductor from the get-go. A lot of engineering firms go, if the size is 1, we'll go higher, right? We'll go jump into a next size from the get-go without messing around because of what? Voltage drop. Voltage drop. Can I have thumbs up, Chad? Because of that voltage drop. Determine the raceway size, the conductor, and then the neutral size. We'll talk about the neutral. We size our neutral based on the unbalanced load. And I told you guys what the rules for the neutral. Up to 300 amp, 225 amp panel for neutral. Don't even mess with it. Higher than 200, 225 amp panel, maybe 250, 300. You start the rating. If you don't know the load, you start the rating based on, remember that 70% of the 200. If you have the load, the actual load, then you just use the load. Cool? So that's what we're going to be, and then sizing the raceways to fit that. Okay, so that's what this is. When you size the ampacity of the feeder, must be not less than the voltage amp, the coincidental loads of branch circuits, and the feeder. So this is if I have my conductor I for the feeder must be equal. This is what this is. I for the feeder must be more or equal to I for the load. You guys have done that. This is just fancy way of doing it. So if you load as a 50 amps, your feeder has to be 50 amps or what? Or higher. That's what we're talking about. By the feeder and reduced by the demand factor. There's some demand factor if it's continuous load, 1.25, and non-continuous at 100%. Okay, only larger or uncoincident loads need to be included. Feeder neutral may be reduced. So when we size the feeder, here's what we do to size the feeder, guys. Very easy. You take 1.25 times I, the current for continuous load, plus I for non-continuous load. And you add them all up and size your feeder. You guys have done it with me, right? This is simplifying it a little bit. When we did the lighting, remember how we did the lighting? We took all our lights and we multiplied by 1.25 because continuous load, and we size our feeder. Can I have thumbs up, Chad? We fully understand how to size a feeder based on the load. Because we have done it for your project and we fully understand it. Cool? Okay. Remember the non-coincidental loads? When we were doing the HVAC equipment, guys, and we said the heating and cooling, highly unlikely they will be at the same time. So what did we do? We picked the largest. That's what this is telling you. You pick the largest. Neutral conductor, neutral reduction. You can do neutral reduction. And I told you a rule of thumb, 125 up to 300 amp panel, full neutral. Higher than that, you derate the neutral based on 70%, or the actual neutral load, Can I have thumbs up, Jeff, for that? Okay, so that's what this is all about. Overcam protection device. Rating shall not be less than the non-continuous load plus 125% of the continuous load. That's exactly what you guys did for me. When we did the lighting panel, here's my lighting panel, 225 amp, and here's my panel, and I put 225 amp panel, and I put, Jeff, what was it, 2 watt or the size that you guys size it? 225. For 225. I think it was 2 watt. Let's say 2 watt, right? So when we size this, how did we size the overcam protection device? Do you guys remember? If you guys remember what we did when we sized the panel, we took the continuous load 1.25 times I continuous. Right? Remember that? We took that. Then we sized the panel. Then we sized the overcam protection device too. And then we sized the conductor. That's what this is telling you. You take 125% of the continuous load plus the non-continuous load. For the lighting panels, all of them are continuous. For receptacle panels, we did not multiply them by 1.25 because they're non-continuous. Any questions, any comments about sizing overcam protection device for feeders? Any questions, any comments? Any questions, any comments? The most mistake let me take this. This is a 100 amp panel, and the feeder is number 1. Cool. And I want somebody to tell me how much load. Somebody to get me how much load can I get out of this 100 amp? Continuous. Continuous. How much? The load is the opposite, 80%. You're right on the right track. So the load, guys, my load here is only 80% of the overcam protection device. What's 80% of 100? 80 amps. This is the most confusing one. The most confusing thing that the people get confused all the time. If you have a panel that says 100 amp, do you think you can pull continuously 100 amp out of it? Continuously for 3 hours or more. You only can pull 80% out of this panel. Can I have thumbs up, Chad? That's why the 1.25 is coming to be. Can you guys see where the 1.2, why they do the 1.25? They oversize the panel. They oversize the panel from the get-go, so you don't get into a panel that has 100 amp, but you can only pull 80% of it. So you start with the load. You take the load. If it's continuous, increase it 25%. Non-continuous, add it 100%. Size your panel. Then you're guaranteed when you size your panel that you can pull the continuous load and non-continuous load at the same time. Any comments, guys? Any questions about that? Any comments, any questions? You can't believe how many people get confused between them. When I say there's 225 amp panel, the one that you guys sized for me, can I pull 225 amp panel out of the panel continuously? No. How much can you pull out of it? Only 80% of the rating of the overcam protection device. That's by code. So, oops, I think I have 225 amp panel. So the question would be, did I undersize my panel? No. Why? Because when we came up with the 225 amp panel size, we already added the factor of 25% extra. Do you guys understand what we're doing? Do you see how important the 25% factor is? Because when your system is up and running, you can only take 80% out of it. Unless it's 100% rated, which is, that's after 1,000 amp or higher, it's slightly different. 1,000 amp switch gear. Can I get 1,000 amp out of 1,000 amp switch gear? Yes, Chad. Why? Because then they make the circuit breakers, guys, bigger, more robust, and they can handle the continuous load for 1,000 amp. Does that make sense? So that's basically it. Temperature limitations. There's temperature limit. You guys remember we went through this one in details. I have a couple of pictures. This is where it's 100 conductor number 1 and 4. 1 through 14, 60-degree column. If the amp 100 or less, 60-degree column. Everything else, 75-degree column. 90 degrees only for the rating. That's what this is telling you. We have a couple of pictures for you when you size. Okay, so when you select the feeder conductor, remember what the feeder is. This book says we can use a lot of aluminum. The first step in selecting is to identify the material. So same allowable size. Are we going to use copper or are we going to use aluminum? Copper or aluminum? Aluminum, advantage of that one is weight and cost factors. So there are 2 options when you choose feeders. You can use aluminum conductor or copper conductor. Aluminum conductor costs less, way less. Bigger conductor though, right? Copper are smaller conductor, more amps, cost more. So which one, as an engineer, which one do you think Chad is gonna say? Copper. Why copper? Less maintenance on the copper, for the most part, less maintenance, and they carry more current, smaller conductors, more expensive, be it you're investing in the future. You're investing in 25 to 30 years future of your company. So, but a lot of companies, contractor guys, will be pushing aluminum on you. So, if you're an engineering firm, you push copper. If you're an electrical contractor, when you get the job, what do? Aluminum, the cheapest, unless they're paying for it. Okay, so that's the first. The first point is which material am I going to be using? Cool. Or the other thing is also aluminum is a big deal, guys. If the weight is an issue. If you want to hang these cables from a structure that's you're not really sure about the weight of that structure, you don't want it to collapse. So aluminum would be highly unlikely, but aluminum would be an option for you. Wire selection, connectors. The connectors, whether it is necessary to copper or aluminum conductors. The other thing for connectors, guys, almost all connectors are rated for copper or aluminum. If you want to put copper and aluminum under the same connector, they have to separate them, and you have to have a special connector that takes copper and aluminum, because these are two dissimilar materials. They expand and contract at different rate, so they loosen the lugs differently, and they eat into each other's too. So what they do, typically, if you have a switch gear, the lugs will be rated for copper or aluminum. Bring it on, torque them, done. If you want to put one cable copper and one cable aluminum, why would you do that? Phase A, all copper. Phase B, all of aluminum. They're sitting at different lugs anyway, so it doesn't matter. Can I do that? Yes. Is that full? Yes. So does that make sense? Let's take phase A, copper, phase B, aluminum, and phase C, copper again. So you can do that as long as the lugs are rated for copper or aluminum. Corrosion, some problem associated with aluminum conductors that we said, corrosion action, if from moisture, brush inhibitors into the aluminum conductor to prevent oxidations too. So that's why when you guys torque it, if you guys torque them, right, to put that little material on it to get you good connections on aluminum. So that's why a lot of people don't like aluminum, guys, because it needs more maintenance. That's all. You just have to put your facility on a maintenance. So every year you have to go to the logs and detect the heat of the logs. If they're hot, you're going to torque them, or you shut down for maintenance and you retorque all your switch gears and your panels done. You know. So if you do it, then you're not going to have any problem with aluminum. Wire selection. Aluminum wire expands. Here's that we talked about, the problem with aluminum: expands and contracts at a different degree than copper. Another possible cause of poor connection. So what's the problem of a wire expanding and contracting at a higher rate? Loading it goes up, under load goes down. What do you think is going to happen to the lug at the end of it? Loose. What happens if you have a loose lug? Arc flash. Anybody knows what an arc flash is? A fire inside your building, inside your panel, right? That's why to avoid this one, what do? Put them on a preventative maintenance program. Maintain them. Measure the temperature of the lugs annually. Retorque all your panels. Done. You can avoid this one by putting them in the poor connection, by torquing them, because over time they loosen up. Go there and torque them. Okay, circuit parameters must be continuous, non-continuous. Now, when we size the cable, I want to highlight a few things. You guys remember table 220.12 when we size all the conductors? And so this table gives you the load. This table, either continuous or non-continuous. This table, conductor be installed, 110.04a tells you the THHN and THHW and so forth. And this one will get you the amps, right? This is where you get T, H, H, N. This will get you amps, amp, right? And you guys have used these. This will get you load. Can I have thumbs up, Chad? We fully understand and use these. You get the load, convert it to amps, then go pick up the THHN, THHW conductor from these. Typically THHN if you're inside, THHW or THHN/THW if you're coming outside, right? Done. And then you go to 310 or 15A and get your conductor. Or the raceway, ambient temperature correction. This will get you the ambient temperature correction, but 310.15B16 will get you the amplicity. 310.15B16, right? This is where you get your amps. I hate to say the amp correction, guys, for that one. The amp correction on feeders, the only correction you should have on feeders is temperature correction only. No bundling. So you get, then this will get you the correction for amps. Correction for amps. And we use that one too based on the temperature. This is just the steps, guys, of feeder connections. They have 5 steps or so. Overconduction device corrections, let's just say 225 amp. Minimum ungrounding conductor, let's say 2 watt, right? Conductor type determine, THHN. Conductor size determined, minimum ungrounded conductor size determination, conductor type determination, conductor size determination. Okay, conductor size determination, the same thing, 2 aught, this is the same conductor. Neutral conductors, as it said, guys, match, I always say match over current protection device up to 200, say, and 50 amp. In the 225 all the way to 300 match over current protection device. After that, we start the rate based on 2 factors. Either the actual neutral load, or if I don't know what the actual neutral load in the panel, what do you do? 70% like you guys have done with me. 70%. Okay, here's a situation where I have a 100 amp panel. This is really cool. I have my 100 amp panel. And can you guys see the neutral conductor here? The neutral is 200 amp. If you don't have it this time, if you have a panel that feeds servers is a room like yours here, full of computers. That's exactly how they do, guys. They make the neutral double the size of the phase because of a word called harmonics. Because of harmonics. The problem, guys, with this system is balanced. This is supposed to be zero amps, right? This is supposed to be 0 amps. But because connecting panel board primarily connected to computer, data processing, and so forth, electronics, this will create harmonics. The harmonics will add up on the neutral. Unlike non-harmonics, they cancel each other. So if you're in a data center, if you're only in a data center, your neutral is going to be double the size of your phase. They do it differently, guys. Not this panel, a data center. So just keep this in mind. There is a situation where neutral will be double the size of your phase because of the harmonics. So instead of 100 add up to a 0, the harmonic will add up to twice as much current on the feeders. So be aware of that one because of harmonics. Another problem that they solve harmonics, guys, you remember the problem with harmonic, they don't add up to 0 like others. Everybody knows what a harmonic is. The frequency that we get is 60 hertz. There's also, if you have electronics, they screw up the voltage to allow 180, 120, multiples of the 60. Signals at multiples of 60. You're going to see a picture of them. So to eliminate the effect on the branch circuits, do you guys remember how we do that? We have a neutral with every phase. That's what you guys are doing with me, right? In this project, there are certain receptacles in that Revit project that require you to have a neutral with every circuit. Why? Because if you have 10 amps, they don't add up to 0 amps because there's harmonic on them. They might add up to 20 amps and overload the neutral. To solve the problem on a branch circuit like this, you just have a neutral with every phase. Can I have thumbs up, Chad? Well, same thing when we do gas lights, a neutral with every light. So solve the problem. So nonlinear load, a little bit about the nonlinear load I'll show you guys. When you do nonlinear load, here's my point, it could have double the size of your neutral. So instead of phase A, phase B, phase C, add up to 0, they add up to double the amount in one phase. How do they do that? I will spare you the math behind that. They just, by design, they don't add up. The reason why phase A, B, and C add up to 0, guys, because we designed it to do so, and we put linear load on it. You put nonlinear load, it screwed up that design of the signal, and it adds up other than 0. So for you, the only thing you need to understand is, number one, size the neutral, double the neutral on the feeders. We only do this, for the most part, only on panels and feeders that feed data centers. We rarely, if ever, do it on lighting panel, receptacle panel. So what do we do, guys, for lighting panel, receptacle panel up to 300 amp? Between 225 to 300 amp. What do you do? Full neutral. Do you know why we do full neutral? Because if we do full neutral, the worst scenario is the neutral will have harmonics and it will have as much current as a phase. So you almost cover the worst scenario. That's why the full neutral, we call it full neutral from here. Okay, nonlinear loads. If the nonlinear load is huge, as in a data center, engineers like yourself, guys, going to specify a K-rated transformers. I want you to understand that the term K-rated transformers. What the heck is a K-rated transformer? Imagine Chadder's transformer. The way they make the K-rated transformer, guys, they make them from a bigger conductors, thicker insulation, more robust, so they can handle the heat generated inside them by the harmonics. Can I have thumbs up, Chad? Who cares? More money. You spend more money for them. So if you have a transformer that feeds a data center, Joe, transformer feeds a data center, the first thing should come to your mind is K-rated transformers. We'll talk about how to K-rate them, but when you, the same thing, if you have a 50 kVA transformer, you're going to buy a K-rated transformer or non-K-rated transformer. If it's a K-rated, it can handle the heat better. If it's non-K-rated, it cannot handle the heat better. So a better system will be K-rated transformer. Okay, K-rated transformer can handle the heat generated by the harmonics. We're talking about a transformer that you own and operate. The utilities, we have no control over this. In this project, we don't have transformers. Next project, you will size a transformer. So remember, what's the key word? K-rated transformers. Okay, voltage drop. We talked about voltage drop, guys. You have, it's actually, it's a footprint on the feeders. You have to size your feeders to be able to handle the voltage drop. If you want to know that you have a voltage drop calculation, you have to check your voltage, but from the get-go. A lot of engineers, guys, from the get-go, they size based on the load and up the conductor one size from the get-go. If you don't want to do that, you do a voltage drop calculation. If you have 100 feet or less, most 99.9% you're good. If you have higher than 100 feet, you have to run, that's my cutoff, run a voltage drop calculation, which we're going to be doing. Voltage drop calculation, which we'll be doing. Okay, for voltage drop calculation, if I may have your attention, my friends, the voltage drop is 5% total. On the feeders, what we do, guys, on the feeders from here to here, you typically 3% on the feeders and 2% on the branch circuits. That's how we divide them. This is how engineers divide them all the time, almost always all the time. So if I have a voltage of 208 here, volt, I can, right at this light, can have somebody have a calculator and get me 208, 0.9 of 208, 0.95 times 208 volt. I have 198. I can have 198 volt, and the equipment, can you guys see that? I started at the service with 208 volt. I can only lose 5 volts, 5% of it. When I reach that load, I only up to 198 volt. That's acceptable. Can I have thumbs up, Chad? That's acceptable. That's unacceptable. So how do you minimize it to 3%? We size your feeders to allow only no more than 3%. And my branch circuit, I don't want to. When I told you, guys, remember the receptacles that we were talking about? And I told you 6 receptacles and 18 lights and all this good stuff. These factors, all the factors that you want to maintain a 2% branch circuit voltage drop. You don't want it to go higher than that. Factored in. Does that make sense? So you want to maintain an operating voltage of this voltage, not lower than 100. What happens if you go lower than that? Equipment will malfunction, will not start, will run inefficiently, will die prematurely. Can I have thumbs up, Chad, for voltage drop? So that's your voltage drop. It's coming. We will do a voltage drop calculation. I promise you on that one. So if you have a problem with the voltage drop, guys, you have, one question would be check with the utilities. So here you go. Andrew, my friend, if you go back here, this voltage is coming from Excel. You have to go measure the voltage at the service. Do you really have to weigh it? Excel might have screwed you and gave you 200, right? If you start with 200, what do you think you're going to end up here? Much lower. So your start point is you, the utility. Can I have thumbs up, Chad? That's your starting point, the utility. The utility guys almost always guarantee you a voltage higher or this voltage, almost always. Methods to estimate the voltage drop. So you get the utilities. Method to estimate the voltage drop, typically size of the conductors and so forth, parallel conductors. Okay, so that's so you start with the utilities, and then you have to go check your distances on your feeders. 100 feet or less, for the most part, you're good. Higher than 100 feet, there and what? Check your feeder. So you have a voltage drop, what do? If it's 1, make it 1 watt, right? Any questions about this? Any comments, any questions? There are a couple of things about parallel. We will do voltage drop calculation. We will do voltage drop calculation. The only thing I want you to understand is the 5%, the 2 and 3 right now. Cool. And the effect of it. Parallel conductors. You guys remember that number here? If your load is 400, higher than 400 amp parallel, you remember what Chad told you that? Over 400 amp parallel. And that goes with a size of 500 kcm. Typically, 500 kcm is allowed to give you 380, which by code allowed to go to 400. So if you want to pull a conductor larger than 500 kcm, always parallel. Why? Easier to install, easier to maintain, and so forth. So can I have thumbs up for this one, guys? If your service is more than 400 amp, always parallel. How many you parallel? When you parallel, how many? The least amount of parallel, the better. So for example, if I have 1200 panel, I can make it multiples of 400. So that will give me how many runs? 3 runs, okay? Could I make it 4 runs? Yes. Is it a good idea? No. Which one is a better idea? When you parallel, make sure, keep this one, you want the feeders to be this amount or less when you parallel. Okay. Here's where you get all the requirements for parallel conductor. We'll talk about these guys. The conductors be the same. Here's the rules for the conductor. They have to be the same length, same different in length. Okay, so the rules for the conductor when parallel, they have to be the same material, same length, same insulation, same termination, and a bunch of other same. Why? Because if you have a small difference in the length, will have a significant difference in the current. The significant difference in current. I'll show you an example later on. Okay, the rest of these guys is schedules. These are panel worksheets, schedule, and load calculation. Remember, this book, Jeff, is following a project. So there is a schedule that they're going through. Load calculation are transferred to the schedule. I'm not going to go through the schedule. We've done our own, guys. Please review it for your own. So they're having a schedule here, and they did the calculation like we did. Okay, and then they talk about the columns for each one of these schedules. Here's the schedule that they use and how they transfer it. And the NDC code book and lining calculation. This is load calculation that they did, and I know you guys did the load calculation with me for the areas that they have and sizing it. So, okay, I'm going to show you a couple of pictures, and then we'll the reason why I moved fast on these, we did a load calculation more thorough than they did. Please read it, just FYI only. They're load calc. They're doing a load calc. Okay, here's the first thing I would like you guys to remember. If you graduate from Dunwoody and you don't understand these 3, oops, why do I go here? The service conductor, right? Here's your service conductor, number 1, number 2, number 3. Everybody understand where the service conductor is bringing the power to the building? The feeders between 2 panels and the branch circuit between the overconduction device in a panel and the last utilization equipment. Thumbs up, Chad? Okay, so when we have a voltage drop, this will be your 2% here, this will be your 3% here, and you're always right at this point, you want 208. You want the utility to give you 208 right at this point, right? If you get less than 208, you have to call Excel because your start point is screwed up. Can I have if your system is 208, if your system is 480, what do you think this will be? Your start point have to be the actual voltage. This is the rules, guys, for termination. I've never seen it written and drawn better than that. I'm going to go over it one more time. Look at this. If the termination here and here 60, 60, 60, this is the assumption for 100 amp or less, or number 14 through number 1. Can I have thumbs up, Chad? If you don't know number 14 through number 1 or 100 amp or less, the assumption is 60, 60 termination unless you know otherwise. Look at the second one. If conductors with higher temperature, can I use these 2 conductors between them? Between 60, 60, yes, but you take the amps based on what? The 60, like you guys have done with me. Okay, if the amps I is more than 100 or conductor is more than number 1, then you can use the 75 because the default is 75. If you have a three-phase equipment, guys, really, if you have a three-phase equipment, yeah, default is 75 by manufacturer because the lugs are rated for 75. For motors, your motors right here, the lugs are rated for 75, so we can size the 75 regardless for this three types of motors, design motors. When we do three-phase, we size based on 75 all the feeders, all the services. The only thing that we size based on 60 is what? Branch circuits. Branch circuits. Any comments, any questions? Any comments, guys, any questions? So this is the termination. We talked about equipment rated over 100, 70, and conductor with higher temperature you can use. So we talked about the default gears here. Please review these nice pictures because it gives you basically the 100 or less, or number 1 through 14, 60, unless you know otherwise. Everything else 75, right? And 90 is only for what? Derating. You guys got it. So that's that one. Okay, this is what I want to show you guys. This is how you want your system to be. This is your 208 voltage. Here's my 208 volt, right? This is your 208 volt signal. One signal out of 60 signals, right? If you have harmonics, look how the harmonics, the 60, here's my 208. This is my 208 at 60 hertz. This is at 60 hertz. Now look what happened. On that signal, guys, there will be all these harmonics will be riding with it. They're all sinusoidal signals. Here's the fundamental. Third harmonic means 3 times 60. Fifth harmonic means 5 times 60. 7 times 60. Does that make sense? And the first fundamental is 1 times 60. Can I get you the 60 is the hertz? Can you guys, everybody can see the harmonic here? 60, each one of them. The third harmonic is 3 times 60, 120 hertz. This is how they look like. Can you guys see that? And when you add them up, can you guys see the orange one, the resultant, how they screw up the shape of your signal? Can I have thumbs up, Chad? We know how to screw it up. Now, who cares? Your neutral will be screwed up. Can I have a thumbs up? This is one of the best pictures that they have, guys, to represent harmonics. Who create this mess here? Electronic equipments that you're looking at right now, computers. Okay? Can I have thumbs up that we understand how the harmonics are riding on it? 60 hertz. They're little signals riding together. When they add up, I don't know if you guys can see, when you take a point like this, take one point here and add all these points together, that's what you get. You get this point right here. Add one point, add all these signals at one point, that's how they came up with the yellow resultant, or the overall. Who cares that your electrical equipment don't like that signal? Electrical equipment love this signal here. Electrical equipment. Can I have thumbs up, Chad? That's how we care about harmonics. Okay, so that's a good example. This is, can you guys see that where we looked at this, the 200 amp neutral, because of these harmonic that's riding on the signal, because of these harmonics. So oversize the neutral. Look at this. If you have a ballasted equipment like this, that's why your neutral could be carrying as much amps. I want to emphasize, guys, can you guys see this? 16 amps and 16 amps. The neutral is also 16 amps. It should be 0, like you studied, right? Why? Because of the harmonic. Remember, it's not sinusoidal. They're riding on the same signal, screwing it up, basically. Okay? So who cares? Make sure you size. What we do here is either pull a neutral with every phase, or oversize the neutral, make it number 10, right? Or if all these are number 12, you're still good, right? Number 12, 16 is good. So don't undersize a neutral if you have harmonics, which almost always you do. Here's the solution. Like we showed you guys, the solution for that one is to pull a neutral. A lot of engineers require a neutral instead of multi wire branch circuits. Here's common neutral. So what they're trying to avoid is having this. Why do we like this, Darren? Because this makes cheaper, right? Cheaper installation. So versus this. So if you have a harmonic, that's what we're specifying in certain areas, is to have a neutral at every phase. This is the common neutral. Talked about the voltage drop. We talked about the voltage drop, guys. Paralleling. Here's the paralleling. When you parallel, I like this picture. Everybody knows that here's paralleling phase A. Let me just say here's paralleling. We have the phase A. Here's my phase A, my phase A, my phase B, and this is my B, and C, C is C, and my neutral, I'm going to put it here. My neutral, my neutral. I could not find a better picture to show paralleling. When you parallel conductor, guys, remember the rule is if you go 400 more, if your amp is more than 400 amp, start paralleling, right? What does paralleling mean? Can you guys see if phase A has two conductors tied to the same lug and another two conductors tied to the same set of lugs? Can I have thumbs up, Chad? We understand? Is phase A and phase C paralleled? Or are phase A and phase C parallel? The phases. The phases are not parallel. The conductor of every phase are parallel. The conductor of every phase are parallel. Okay, any question, guys? So you have to have the same length, the same conductor material, cover aluminum, circular mill area, same insulation type, THHN, terminated in the same manner. And if they're running in the conduit, separate raceways. If they're running in the conduit, the same conduit or same cable. Any question about paralleling conductors? Can I have thumbs up for that? One of the nicest pictures that can get you about paralleling conductors. Okay, the rest of this, guys, is sizing based on the calculation that they did, and we did our sizing. Here's the load calculation that they did for their lighting. The same thing like we did, guys. The number of lights. I'm not going to go over this because we did the load calculation ourselves. You basically, for lights, you take a volt amp if it's office building, 1 volt amp times the square foot of the building, size based on that one, or the actual load, whichever is larger. And that's what they're doing. So you review that one on your own, buddies. Okay, any comments, any questions? Any comments, any questions? Let me see here. Any comments, guys, any questions? So please, all these guys, Andrew is supposed to get you to emphasize, we keep repeating the same thing almost over and over, to stick in as we move forward. So if you guys don't have any questions, I would like to give you 5 minutes exactly, and I want to go over pole box calculation. And then I'll let you work on other things. Go get your coffee, get ready for half an hour box fill calculation. Or pole box calculation.